Lasers become part of our daily life with applications in fields as diverse as medicine, entertainment, telecommunications, defense, and manufacturing. The use of high-power laser tools is increasing every year. Billions of small and large parts are processed every day by using lasers. But what happens if at least one laser machine fails in a production line? It blocks the continuous workflow of the entire factory. The downtime of laser-based operations in mass production is extremely costly and must be avoided at any time. However, it's not always clear why lasers fail and how to avoid it. Let's take a closer look into the laser to identify potential problems. Laser systems are optical chains made out of many links. Thus, every laser is only as strong as its weakest optical element along the optical path. Small damages are initiated when a built-in optic such as a mirror, lens, prism or crystal is exposed to strong laser light. Optics tend to degrade over time, turning from small damages into large craters. This is one of the main reasons why lasers fail or don't work as expected, thus causing a whole production line to stop. To avoid laser damage in lasers, it is necessary to operate them below the so-called laser-induced damage threshold. However, to improve laser power, it is needed to improve the damage performance of built-in optics. The first step to do that is to understand why optics fail under intense light. Next, identify limiting factors and remove them if possible. To produce classical optics from glass, they are first cut using abrasive tools. Mechanical cutting and grinding are destructive procedures which cause the formation of cracks below the surface, the so-called layer of subsurface damage. Cut pieces are blocked together in shaping mechanism and mechanically rounded. New cracks of subsurface damage appear at the edges of glass pieces due to the brittleness of optical materials. The nature of the subsurface damage depends on the type of glass processing. To reach optical surface quality and minimize the effect of subsurface damage, a polishing procedure is applied in multiple steps. Small abrasive particles are used to make the surface smooth. Due to the chemical-mechanical interaction between the polishing particles and the workpiece, a thin hydrated layer is created on the top of the glass. It is known as the Bilby layer. Subsurface damage and the Bilby layers are common for all types of abrasive polishing processes. These layers hide many defects with localized absorptance. The required spectral properties of optical elements are achieved by thin films. The deposition process might also introduce nodular defects, also well known as laser damage precursors. Finally, optics can be contaminated by the environment where it is stored or operated. All these objects are potential sources of extrinsic optical damage. As optics, manufacturing technologies are very different. Not all of them are optimized for high-power lasers. Sometimes damage might appear accidentally at a much lower irradiation level than anyone would expect. Thus, it is a good idea to choose optics wisely by getting real numbers. At Lidaris, the damaged performance of optical elements can be tested for various wavelengths, pulse durations, and environmental conditions. Testing capabilities cover continuous wave, nanosecond, picosecond, or femtosecond irradiation in air or vacuum environment. Depending on the optics type, size, and aim of the testing, different testing protocols might be chosen. Lidaris provides standard one-on-one, S-on-1, pass or fail certification tests, as well as non-standard testing procedures. R-on-1 testing can be done on small optical elements. Raster scanning or optics lifetime estimations are also available. Furthermore, if that is not enough, Lidaris team is always up for small and large-scale R&D projects. Finally, even the best optical technologies sometimes fail, as not all manufacturing processes are repeatable. Thus, to avoid laser damage, it is always a good idea to certify optics within or between production batches. For instance, if a bad optics production batch is used to manufacture 10 laser systems, it will require fixing of 10 laser systems in the field. The pass or fail testing of every optics production batch can help to prevent that. Certification of optics, if done right, minimizes the maintenance costs due to reduced risk of unexpected failure in field applications. Thus, whether you manufacture, sell, or use optical elements, it is important to check if those elements actually meet their promised specifications. Lidaris is a company that helps understand, test, and improve the damage performance of your laser optics. A dynamic team of Lidaris experts is trusted by more than 150 optics leading companies worldwide for more than 10 years. Expertise in laser damage, fast turnaround service, detailed measurement reports, and a variety of available testing approaches make Lidaris an attractive partner for reaching better damage performance of optical elements. Testing optics at Lidaris helps to certify your optics quality prior to use by getting real numbers. Select or best vendors or optics manufacturing technologies for a specific laser application. Figure out why optics failed and if there is a space for improvements. Contact Lidaris by booking an online meeting with a Lidaris expert if you want to learn more about how laser damage can be avoided or improved. Lidaris makes lasers work.